So the floor is yours.
All right, so thanks so much for this opportunity, and well, it's great taking part in this seminar. And so I thought I would talk about Gorenstein polytopes. Just recently they got again new interest because of a breakthrough result originating somehow in this group, like with Johanna and Karim and Stavros Papadakis and Vasiliki Petrotou. They proved something that was conjectured long time ago. And so I will just briefly also mention this. Overall, I will try to tell you about results that have been proven about Gorenstein polytopes, so open question like related to some recent work. And so, well, here's the overview of the talk. Give you some survey of characterization of Gorenstein polytopes, because I don't assume everyone knows about them already. I hope I'm not totally wrong here and people just drop out. But anyway, I think it's important to recall this when we will talk about a notion that is not so well known about reducibility of Gorenstein polytopes. Then I will talk about the invariant coming from Ehrhart theory. And that's like it also kind of I think at the moment again there are some interesting developments there, and finally about a notion called thinness, whatever it is. So let's just start, and let's start right somehow at the beginning of this. So for me, a lattice polytope is so just to make clear what we're up to here. So lattice polytope is a polytope in dimension d, and the vertices should all have integer coordinates, so in z to the d. And typically d will also be the dimension of the polytope. So if I don't say anything, in most cases there shouldn't be lots of ambiguity. D can also be just regard to the dimension of the polytope. And so here I've seen that Victor is in the audience, which I'm very happy about. So here's the famous notion of a reflexive polytope. And so that's a lattice polytope, which you should assume is full dimensional, has a zero in the interior. And in this case, and then one can define its dual polytope. And this dual polytope should also be a lattice polytope. So let's do an example here. So let's say we have here our standard. Well, so this polygon here, like that one. So very simple one, so I can simply draw it. And so what's the dual polytope? For that, you look at the facets, and it's their hyperplanes. And in this case, we use some inner normals. So we have an inner normal according to that hyperplane face. So that's facet. It's like UF, let's say. And then if you draw that in the dual space, and so this has to be somehow normalized, right? We have to say which one it is, how long it is. Well, we normalize it so that this evaluates to -1 here. Okay, so it evaluates to -1 on this hyperplane. And in that sense, where we got a unique linear functional, and this is one of the vertices of the dual polytope. And if you do that for all the facets, you get all the vertices here. So we get this guy. Someone still now using the red mode. No, doesn't matter. Okay. So. And we use this X just because later we will have P star, like there will be stars around, and I just want to make sure it's not really a totally canonical notation. But I hope no one is offended by this. So, all right. And so in general, like, you can do this for any polytope. You don't need lattice polytopes for this. As long as you have an interior point, you will get a polytope out of it. And so, for instance, if you will make this polytope larger, then the dual one will get smaller. And let's see that it won't be a lattice polytope anymore. The vertices will have rational coordinates. And so somehow this is a very nice balanced out condition to have on both sides lattice polytopes. Of course, you cannot make it here smaller, then it would not be a lattice polytope here. So somehow on both sides is a nice balanced out. Okay, so this is the definition of a lattice polytope, that P and P dual are of a reflexive polytope, that P and P dual are lattice polytopes. And also in this talk, somehow I just noted this here because sometimes there come questions regarding to this notion. If you move a reflexive polytope around so that the interior point might be a different lattice point, that's for me also okay. I would still call this a reflexive polytope. Okay, if any questions, just ask. Okay, so here are some facts about reflexive polytopes that turn up in pairs. So that's what we see in here. So this is this nice duality involved in reflexive polytopes. That's like if you think about toric geometry, then there's a unique correspondence to so-called Gorenstein toric Fano varieties. Simply by what you do is you, maybe let's use it. Do we have a different color? This one here. If you take the code to take the fan spanned by the faces here, right? If this is the fan spanned by the faces of P, then this defines a toric variety. So here so toric variety, and this toric variety, so projective toric variety, and if you look at its canonical divisor. And that is essentially given or determined by this dual polytope, in the sense that, for instance, the space of global sections has as a basis the lattice points of this dual polytope. And so this will be an ample Cartier divisor, and that's essentially the definition of Gorenstein toric Fano variety. Well, we don't actually need. This talk will be quite combinatorial, so we don't need much about this here, but this is so this is one of the ways to think about reflexive polytopes. So the motivation by Victor and together with Kofel or Borisov was to use this duality, and of course there's a long backstory to this, and Victor should really talk about this, but it's just important that I mention this as a motivation, is that that you can use these with polytopes, so the correspondence to the toric Fano variety side, to find anticanonical hypersurface in there, right? You can just, for instance, very naively, you can take a polynomial consisting of monomials corresponding to these lattice points, and you take generic coefficients, and that will give you an anticanonical hypersurface, a generic one, which will be in itself will be a Calabi-Yau variety, or a singular one. And then up to some several issues involved in there, but essentially the idea is if you take in there these hypersurfaces and do it on both sides, then a conjecture proven by in the famous paper to have, like, at least on the level of Hodge numbers, do we have satisfied certain mirror symmetry coming from theoretical physics. So I will say a few words more about this later. For a moment, just like as a motivation. So that means, like, that's one of the reasons also why physicists got very much excited about this, about reflexive polytopes. From a combinatorial viewpoint, the important property for us to have is that they have precisely one interior lattice point, and that can be easily seen here because if you take this facet F and it's and the inner normal UF, which evaluates to -1, and that of course evaluates here to 0. And that means any lattice point between these two, between this strip here, and the strip will have to satisfy, if it's evaluated with UF, which is a lattice point, that's our condition, this is a lattice point, to an integer. Meaning that, well, if it's an integer between 0 and -1, can only be 0 or -1. So there are no lattice points in here, and you can completely cover the polytope P by these strips. So the only point interior is the only point possible is the interior point is the 0, the origin. And so this situation where you have no lattice points between these two parallel hyperplanes, this is also often referred to as having lattice distance 1. So this is lattice, no, sorry. So refer to this often as having lattice distance 1. Okay, this means they have just one interior lattice point, and therefore there are only finitely many of them in each dimension. Up to some, of course, you have to say talk about isomorphism. So here it's unimodal equivalence. The isomorphism simply means that these are affine lattice automorphisms. So if you have a vector x, and you maybe x plus b, so b you can translate by a lattice point, and the linear map should be an invertible over integers. So the inverse matrix should also have integer entries. So in particular, like this has determined plus or minus 1, so volume is preserved, and of course lattice points the number of lattice points is preserved. And so we have these theoretic results, and there was this huge activity there around 2000 to classify them in dimension 4, which was an interesting case because then the Calabi-Yau is dimension 3. And we found so many of them. It's still, I think, even up to now, one of the largest classifications I'm aware of in the case of lattice polytopes. It was really a big endeavor. But interestingly, from a combinatorial viewpoint, even if I only find many of them in each dimension, you will find any lattice point in them, any lattice polytop among them. Well, not really among them, but among a face of them. So any lattice polytop is really a face of some really probably much higher dimensional reflexive polytop. So you kind of completely, in some sense, cover the whole space of lattice polytops using reflexive polytops. So that's what I wanted to say about reflexive polytops, like the crash course on reflexive polytops. There's still open questions about them, and they are quite nice. Okay, so what about Gorenstein polytops? Well, Gorenstein polytops is just in some sense a slight generalization of reflexive polytops. We should think about them as divisors of reflexive polytops. So the definition is that it's a lattice polytop P such that some multiple of it is a reflexive polytop. So for instance, if you take the 0, 1 square, so 0, 1 square, and you multiply it by 2, well, you get this one here, larger 0, 2 square, this one here. This would be now 2p. That is p, the bigger one is 2p. And we see that this is up to translation. Well, if we move the interior point, if we move the interior point to the 0, this will be a reflexive polytop. So this is precisely one of them. But this is just the example before. So this little square here, this is a Gorenstein polytop. So P would be a Gorenstein polytop. And it would have codegree 2. Someone says index or codegree. Here I use the notion codegree. So the codegree is 2, meaning that you have to multiply by 2 to get a reflexive polytop. So if R is equal to 1, then we are just talking about reflexive polytops. Well, it's just nothing else. But if it's bigger than 1, then some multiple of it is reflexive. Now, this multiple of it has precisely one interior lattice point, meaning that you cannot have any interior lattice points in the original Gorenstein polytop, in the smaller one. If you would have an interior lattice point, you could just use that to make it larger, and then would immediately get lots of interior lattice points. So clearly, it means it doesn't have any interior lattice points, and you the first one you really got one is actually once you are multiplied by R, so you have your reflexive polytop. So this R is unique. So the R is unique. So this codegree is unique. So these Gorenstein polytops appear actually naturally in algebraic, especially in algebraic combinatorics. One studies like combinatorial structures during commutative algebra and via commutative algebra, like the bulk of polytop, all the polytops, and many other combinatorially defined polytops. You can ask yourself, is it a Gorenstein polytop? And in many interesting cases, it will be. And so you see the notion of Gorenstein in many cases once you look into the literature. So now reflexive polytops were defined by a duality, right? So now you seem like to be in a bit of trouble because you don't have an interior lattice point. So how can there be a duality? Because you can't really define a dual polytop right away naively. So the trick is simply now to go to the cone over the polytop. So let me draw it maybe at first here. So you take your, like this, you take your polytop. In this case, let's look at our square. And you put it into a hyperplane, namely the hyperplane, let's say, so of course 1, and you take the cone over it. This cone is denoted by CP. That's how you always do it. And so now you have your cone, and for that cone, there's a dual cone, right? There's the notion of a dual cone, and so I don't really draw it correctly, right? It doesn't really matter. Typically, it's written like this, but essentially, it's just the same definition as before. So you have a dual cone, and now what you can do is, as is a rational cone, so they are generated by, or they are lattice points. So, there are lattice points in each of these rays, and you take the first ones. Now, what typically would happen if you would do this for any kind of polytope P, which you plug in here, so this is your polytope P cross 1. What would happen? You would get something which is full dimensional. If you take these lattice points and you take the convex hull of these 4 lattice points I'm drawn here, you would get a, like, I don't know, a tetrahedron or something, but it would in general be not, it will be full dimensional. So the dimensions won't really fit. But in the case where we are, what we are looking at here, let me actually get this. A second. No. In the case we're looking here, what will happen is that they will lie all on a plane. So picture is pretty bad. They will all lie on a plane. And if you take the convex hull of them, so you get a 2-dimensional polygon again, and this specific example. So in general, so this will always happen if you start with a Gorenstein polytope. And not only this, but if you took this hyperplane and you look at the parallel hyperplane through 0, this will have lattice distance 1 again, just like over there. And so this is now the characterization via duality. So here's that's all again. Let's go through this. So here's the cone, and P is a Gorenstein polytope if and only if the dual cone is also isomorphic in the sense of phenomenal equivalence to the cone over a lattice polytope. So it's also of the form that this ray, the lattice points, the first lattice points on the rays, the convex hull forms a polytope of the same dimension, and it also has lattice distance 1 from the origin. So it will also be of this form. And that means this Q now is precisely what we call the dual Gorenstein polytope. And we denote it also by the same symbol. Okay, so right. Okay, so this is what I denote now by this symbol. And actually, I think it would be really better to call this. Okay, so by peak X, we now denote for a Gorenstein polytope this dual polytope, and it will also have the same codegree. And it will again be a Gorenstein polytope. So this is the theorem that this is equivalent to being Gorenstein. Okay, and so again, we get a nice natural duality. If we have a reflexive polytope, this will just recover the old duality back. Okay. There's another one, because of the word Gorenstein, if you work in algebra, algebraic geometry, you, of course, you have some, you know, probably more about this than I do. And so if you have a lattice polytope, you look at the semi-group algebra, so the one given by the lattice points in your cone. Yeah, so you can just, this is a monad algebra. And this is, well, a nice algebra. This is very famous, that it's a Cohen-Macaulay ring. And it has also a canonical module. And that canonical module is given by ideals of spent by the interior lattice points in your cone. So now you know, don't look at all the lattice points. So essentially, like the way to think about it, this is like CP and this. Take only just interior lattice points. Okay. Now, what's the equivalence? Well, the equivalence is how you think. If it's an algebraic notion called Gorenstein ring, then this is precisely equivalent to P being a Gorenstein point. So this is exactly the same. And essentially, like the link to this is given by this canonical module. So the fact is that for Gorenstein polytope, you have your polytope here and you multiply until you have a reflexive polytope, let's say here, then all the lattice points in the interior, you find them by just shifting your cone again, so that this point in the interior, remember it's unique because RP is reflexive. It's at the apex of this cone. And now all the lattice points in there, if you now just take the lattice points in here, in your from original cone, you just add it to this, you get just, well, you get just all the points in the interior, and so forth. Again, drawn badly, but I hope the idea is clear. So this is given by this identity here. The interior points are given by x plus the lattice points in the cone. And this also is equivalent to a nice reciprocity using Stanley reciprocity or other arguments on the Hilbert series of your semigroup algebra. Well, it's graded, you can count the number of lattice points in there or corresponding to the dimension of these graded pieces. And I should save this. Okay. And so that means now, well, let's look at this Hilbert series again. We all know what this is. I mean, if you've heard about the Ehrhart polynomial, well, we're looking at, we have P here, P cross 1. And now we have here, what do we have? We have 2P cross 2 and so forth. So counting lattice points in these slices is, of course, just counting lattice points in dilates of P. And if you look at the generating series, this is the Hilbert series, and it's a rational series, and the numerator polynomial, that's a really interesting one. So it's typically called H star polynomial. Lots of times it has also been called delta polynomial, or delta, and the coefficient vectors for H star vector or the delta vector. And it's a polynomial, and the most important result here is that it's not only that it has integer coefficients, but non-negative integer coefficients. And the degrees at most, the dimension. D here, really one has to be, here I really think of D being D dimension. Okay, because if you look at the Ehrhart polynomial, just looking at the polynomial, if you count dilates, that's not so nice. It has rational coefficients, sometimes even negative ones. Here you really just get integer, non-negative integer coefficients. Now, this degree of this polynomial, as said, it can be at most d. That's what we call the degree of the whole polytope. Okay, so it has nothing to do with the degree in the sense of algebraic geometry. It's really the degree of this polynomial, and the co-degree is given by this invariant. Namely, you take your polytope and you take the first time that you have an interior lattice point. If you make it larger, yes, you look at it, no interior point. Make it larger, still no, and still until you finally have an interior point. And that means how much you have to dilate, that's this co-degree. Let me see an example. For instance, if we take our little square, the 0, 1 square, then H star of P is 1 plus T. And so the degree of P is 1, and the co-degree was 2, right? We have to multiply by 2. Now, these two, as the name co-degree kind of hints at, they are related. That's just reciprocity, namely, the degree plus the co-degree gives you always the dimension plus 1. You can compute the one from the other. In an example we just had, the degree was 1, the co-degree was 2, that's 3, and of course, that's 2 plus 1. Dimension was 2. And so this degree can vary. It can be at most d. That's the dimension. That happens in like the generic case. Like if you have interior lattice points, it's just the same thing. But if you don't have interior lattice points, like for a little square, the degree drops. It doesn't have dimension 2, but in that case, but dimension degree 1. It doesn't have degree 2, but degree 1. And it can drop as most as if it just has degree 0. If you just have a constant, then that's like really in this case, that's equivalent that the H star polynomial. It's really simply 1, just the one constant 1. So the constant coefficient is always 1. Like if you know the constant coefficient by H0 star, then that is always. And moreover, what's also interesting to note is that the sum of all the coefficients, remember they're all non-negative. So what you get if you plug in 1 into your polynomial, that's what's called this normalized volume of your polytope. Because you know about it. So if it's 1, then that's only the case if you have a unimodular simplex. Unimodular simplex simply means you have a simplex and the lattice points, so the vertices, they form an affine lattice basis. So if you move one of the vertices into 0, the other ones form a basis of a lattice basis of z to the whatever the dimension is of that affine hull. So in that case, z to the 3. So that's a unimodular simplex. That's the smallest thing you can get. So it's as small as possible. It can't get any smaller. It has the smallest possible volume of a lattice polytope. Okay, so this is the characterization here for unimodular simplex. And wait a second, what about Gorenstein polytopes? Well, we talked about this reciprocity of the Hilbert series. Well, if you have a Gorenstein polytope, it's the same as the H-star polynomial palindromic. So it's symmetric. So in other words, look at our example. We had 1 plus t, and so that is palindromic. Everything with respect to the degree. So here with respect to the degree. Both of them are coefficient 1. Okay, any questions so far? So now we also have this characterization, and that's essentially it. And I watched it right through, I was hinting at, and everyone's talking about, well, for that, let's look at one of the first results in this direction, which was by Thanasiadis, who proved that the H-star vector of the Birkhoff polytope is unimodal. And so this was shortly after generalized, but not without giving first some examples that one has to be careful about. I told you that Birkhoff polytopes are with Gorenstein polytopes. And so you might ask yourself whether Gorenstein polytopes always have unimodal H-star vector. And remember that unimodal just means the coefficient vector somehow gets up and then gets down. Since it's symmetric, it really goes up to the middle and then it gets down again. Or maybe it stays the same a while, but doesn't matter as long as it's increasing and decreasing, or non-decreasing, non-increasing. And so there was this example given by Mircea and Sam that there are actually examples that are non-unimodal. There were some conjectures around maybe they are always unimodal, but no, they are not. And we need some assumption on this. And so by Brooms and Römer, they proved that if P admits a regular unimodular triangulation, then it's really unimodal. And so, the Birkhoff polytope satisfies this condition. And so, well, unimodular triangulation is such a triangulation where each of the little lattice polytopes in there are just unimodular simplicity, so the smallest possible. Regular is this famous notion that essentially comes from a projection of if you lift your points up of this standard construction, that it's given in this way. I guess everyone of you who heard about this knows this. And so, yeah, and so the conjecture, what was the conjecture around? The conjecture could you actually relax this to IDP. So maybe I should say a word about what does IDP mean. And simply means that in the cone, if you take a point here on height h, say y, then that can be written by that you then find y1 h points, so y1, y2 until yh, lattice points on height 1, so that y is given as the sum of them. So in other words, if you have a point in the multiple of your lattice polytope, let's say in the 5th multiple, you find 5 lattice points in your polytope that add up to this lattice. That is IDP, or it has several names. It was a long time called integrally closed. Before it was called normal. Nowadays we call it IDP, so integral decomposition property. And so, and they this is this breakthrough result. They prove that if IP is IDP, then the H-star vector points in polytope is unimodal. So this was essentially part of a conjecture of Stanley about standard graded Gorenstein integral domains. One last comment about this. So I don't want to talk more about this. Of course, it's not my story. So, but I definitely have to mention this here. And so one just word here, because if you look at the proof, I always talk about reflexive polytopes. Why is that the case? because if you have an IDP Gorenstein polytope, there's always a way how you can actually project it down onto a reflexive polytope that has the same H star polynomial. Okay, so just in that example, for instance, we had 1 plus t, right? And as a Gorenstein polytope, can you find a reflexive polytope with that H star polynomial? Well, if it's reflexive, the degree is a dimension, so it has to have dimension 1. Otherwise, it doesn't fit. So we need a reflexive polytope of dimension 1. Well, we can just take the interval here, right? From, let's say, minus 0.01. If you take that interval, then the reflexive polytope will precisely have this H star polynomial 1 plus t. So it's always possible to do this. And it's just a little word of caution. This is wrong without the IDP assumption. If it's not IDP, you can easily find Gorenstein polytopes, and there won't be a reflexive polytope with the same H star polynomial. So it would really, so if you forget about IDP assumption, really things become much more complicated. So one cannot, in that case, one cannot just reduce it to the reflexive polytope case. Okay, so this was like the first part of here. I hope I'm okay with time. A little bit slow maybe, so catching up. So the next part is, so we talked about this degree, right? And the degree of a lattice polytope is a good measure for its complexity. So somehow, this, if the degree drops, then somehow the complexity also should get more special. And the question is really, how can you go about higher dimensions? And one observation is that if you take a lattice pyramid, the H star polynomial doesn't change, so the degree doesn't change. So that's always an easy way how to get to higher dimensions and to get lattice polytopes. But they have really high dimension, but the degree is very small. Remember, this is something very special. It means like the Jacob degree is very large, meaning you can multiply a polytope lots and lots and lots of times until you finally get something with an interior lattice. And so the question somehow is, what about the converse? And this was proven by Victor in this following form. But so you take a lattice polytope of dimension d in degree s. If your dimension is bigger than some number that depends on the degree and the normalized volume, so the sum of all the coefficients of the H star polynomial. So in particular, if you fix your H star polynomial, you're only interested in lattice polytope of having this H star polynomial, let's say 1 plus t, and you want to know what happens in higher dimensions, then from some point onwards, it will just be lattice pyramids. So in some sense, not interesting. So you only tells you that you only have to go to a certain finite dimension. There are only finitely many dimensions where something interesting happens, and there are lattice polytopes with this H star polynomial. After that, that will be just pyramids. So this result was generalized. Namely, what one can do is what one really just needs is the leading coefficient. So HS star is the leading coefficient of H star polynomial with respect to the degree, right? And so that's enough. And so if you fix the leading coefficient and you fix the degree, then from some point on it will be a lattice pyramid. And that's good news. Remember, we have a Gorenstein polytope. If P is a Gorenstein polytope, we're interested in them. Then what is HS star? Well, we have polynomicity. So this is H0 star, right? But that was always 1. Meaning, in this case, for a Gorenstein polytope, the degree is an important fact. That's really important. So if the degree is fixed and you go to some higher dimensions, it will be a lattice pyramid. That's what we get out of this theorem as a corollary. The given bounds, however, were very bad. So if you get out of this proof, you get really bad bounds, like doubly exponential or something. Now, so here's what I summarized this. So there are only finitely many Gorenstein polytopes of degree S that are not lattice pyramids. So why that? Because from some dimension, we only have to look at finitely many dimensions, right? In each dimension, we only find many reflexive polytopes. So finitely many Gorenstein polytopes. Remember, these are just divisors. So that's it. So I can actually classify Gorenstein polytopes by the degree. This was done for degree 1. We get just 2 of them, the interval of length 2 and the unit square. We've seen both of them already. For higher, so that's it. For degree 2, this was done by Batyrev-Juny. There are 37. Here are the dimensions, how many you have. And you see it goes up to dimension 5. And so we see that if I have degree 1, starting from dimension 2, starting from dimension, the largest dimension you can get is dimension 2. So from dimension 3 onwards, nothing will be only lattice pyramids. And if degree is 2, starting from dimension 6, there will be only lattice pyramids. And so they conjectured, I call it now the BJ conjecture, just to give it a name. So by Batyrev-Juny in the paper, they conjecture that if P is a Gorenstein polytope having dimension at least 3, at least 3s, then it's a lattice pyramid. So this would be a sharp bound, and so last year I essentially approved this, and so well, in this year in the archive, and so the proof is actually not so difficult. I will just tell you about in the following the most important notions that were around and are used in the proof. I will mention and explain. Of course, the most important notion when talking about lattice polytopes in high dimension are Cayley polytopes. This is the one construction to get interesting examples, or kind of interesting examples, in high dimensions. How does it work? Well, here, let's look at this example here, and then I can explain everything. So, but what it is, a Cayley polytope is simply we have a lattice projection onto a unimodular simplex. So down there we have this little triangle. This is our unimodular simplex of dimension 2. It's just a lattice polygon of volume 1/2 in the case area. It's a normalized volume 1. And well, a unimodular simplex, the only lattice points are the vertices. And that means if you have something like this, it will always project onto the vertices, and you can look at the fibers. So let's call this fiber P1, this one here P2. And this one here, P3. And then we say that P is a Cayley polytope, you write it with a star, P1 star, P2 star, P3 star. So it's a Cayley polytope of these 3 polytopes. And so to make this, there are no trivial cases, this M, so M will be the fiber dimension. So you project down, and the difference of the dimensions, that's this M. So in this case, we project down 1 dimension. And so that means all the lattice polytopes live in this fiber dimension. So we will have all these are 1-dimensional polytopes. So this should be at least 1, so it really project down, and at most d-1, otherwise we just project onto a point. So it's also not interesting. And that's what we call the Cayley polytope. So it's a way you can also make this constructive. You can take, let's say in this case, you can take some lattice polytopes in a certain dimension. You can just put them together. It's not hard to define this, so that you just put them over each of these vertices. And then you get a Cayley polytope in higher dimensions. And the important fact here for us is that the degree is essentially wait a second. Okay. So well, it's not really wrong to do this. So the degree is at most m. So it means, like, if you take, let's 10 polytopes in dimension 3, put them together, get something high dimensional, but this high dimensional polytope will have degree at most 3. So it's, in this case, this lowest prism, so that's its name for it, has degree at most 1. So here's another example. You go in dimension 2, you take these 2 intervals, so it doesn't have to be full dimensional, so P1 and P2, P1, P2, you put them together as a Cayley polytope, you get this guy here. So this projects now onto this 1-dimensional unimodular simplex. The fiber dimension is 2. Right, this is and the fibers are P1 and P3. And so Cayley polytope Cayley polytope just means that it's a lattice width, has lattice width 1. Right? So the distance is 1. And the same thing up here. Also, this has lattice width 1. Can put them also between 2 hyperplanes of lattice distance 1. All right, and now if this is a construction to get in high dimension examples of lattice polytopes with small degree, you can ask, what about the converse? And also, and this was proven. So if we have a lattice polytope in high dimension, then it's whose degree is small, so S is the degree, right? S is the degree. Then it's a Cayley polytope. And but this conjecture, this bound is actually shouldn't be sharp. We don't think it's sharp. The strongest conjecture is what I call the Cayley conjecture, namely that D greater equal than 2S should be the correct bound. It's a very hard problem, I think, to prove this. So it holds for smooth lattice polytopes. There's much more holds there. And there are some other cases, but in general, maybe it's wrong. But it's still, there's no counterexample found. Now, what about Gorenstein polytopes? Well, actually, we can easily prove that if you have a Gorenstein polytop, then P is a Cayley polytop. And so, well, what's kind of the idea behind this? Behind the proof. We'll just quickly say a few words about the proof, so at least some ideas. So we of course we look at CP and we look at the dual cone. That's this or that notion that we like. So we have here the dual polytop, and the idea is somehow to we know that a multiple of it is has an interior lattice point, precisely 1. And what you do is you do this trick that you can essentially, one should really zoom in here somehow. Can I do this? No, it doesn't really help because the pen also gets bigger. I have to get out of this again. Sorry, I dropped myself into some problems here, but I will hopefully be able to solve them. There we go, that looks better. Okay, so what you do is you look at a simplex containing this point, so there will be some parallel pipette over it. I will talk about parallel pipettes in a second. And say, then you take the lattice points in there, in this parallel pipette. So you have this parallel pipette and you have these lattice points in there. And you take them and the vertices together to get up to that point, so that unique point, which is in the interior of that reflexive polytop. So you add them all up so that you get there. So you get several of these points. So something like, if that's point, let's call it y, and we have now these points, let's call them y1 up to yl. Was there more technicality there, but that's, I just want to give you the idea. So these are lattice points. Then how do you get this, show that it's a Cayley polytop? What you do is, you look at the following projection of P. Namely, if you take a point x in P, you project it to, you use these lattice points and just take this map. So you just take, essentially take a matrix multiplication, you just take the scalar products with evaluations with y1 and up to yl, and that will do it. All you have to show is that this will really lie in a unimodular simplex, and that will essentially give you the proof. Yeah, some kind of stuff you have to think about these bounds, and where do the 2s come from. Essentially, the main idea here is, again, that in such a polar pipette, and we'll see this in a second again, the height, the largest height you can get in there of a lattice point, and for that you have to take out the opposite ones. So we're only looking at the half-open polar pipette, and the highest lattice points there are, the height is bounded by S. You can never get higher than that. This is always simplex case, so you have to kind of think about having some polytop, but that's kind of the main idea. So you bound these lattice points, and somehow you try to reach by adding them up this point here, and then you can use that to define a map. So it's just roughly the idea, so you can get an idea of a flavor there. Okay, now what I kind of conjecture is that some of the Gorenstein polytops is very nice, but one can do more. One should be able to do more. I cannot prove. So if you have, and I think this is really like the Cayley conjecture for Gorenstein polytops. Like I call it a refined BJ conjecture, namely that if a B is a Gorenstein polytops, now again, like here, you have the same bound, then it should be reducible. So this is now where reducible comes in, and I want to define this now. And I reduced like lots of time for this, but let's see. Okay, so for that we need to tell you what a kind of a reducible means. We have to need a few more notions. They are not complicated, but somehow you have to keep concentrated on this notion. So we have a Cayley polytop, and there's a notion of a Cayley join. Cayley join means it's not only Cayley polytop, but it's also a join in the combinatorial setting, meaning that if this is a Cayley polytop of, I don't know, P1 and P2, like in our example above, then this would also be a Cayley join, because the dimension here, both factors have dimension 1, you add them up, you get 2. The whole thing has dimension 3, and so 1 plus 1 equal to 3 minus 1. So they are as far apart as you want them to. So this is a Cayley join. However, if you take our little unit square and you take P1 here and P2 there, also this is a Cayley polytop, right? Lattice width 1. That's not a join because the dimension 1 plus 1 will give you 2, but here we really need like 2 minus 1. So we need 1. So this is not an example. If you have a Cayley join in general for Cayley polytopes, the lattice points always lie because of this lattice width 1 thing on one of these two factors. That's important to keep in mind. Okay, so what are examples of Cayley joins? Well, lattice pyramids. So we talked about lattice pyramids. Actually, no one asked what a lattice pyramid is. I just introduced it. Well, it's a pyramid. But the important thing, and I didn't mention this, I forgot about this, is that here we have lattice distance 1. So the apex of your polytop over the base should really have lattice distance 1. Now you cannot take it far away. Then it's not what I call a lattice pyramid. Then it doesn't have this nice property that its start point stays the same. So that's one example, right? You can just easily check this is what's the example of a Cayley join. And you can also take a free join. Free join is the strongest conjecture, the strongest construction we have for higher dimensions. It's really strong. What you do is to take your two polytops. It can just even be the same one, like here. Let's take P1, P2. And you put them in orthogonal and skew orthogonal spaces. So you take P1 here. Let's take here's P1. And we take P1 cross 0 cross 0. And now we take P2, and we could take 0 cross P2, right? But we also want them not to intersect these affine, their affine halves. So we also take them one up. And so it will look like this. And then maybe we can take this one here. So that's this guy. And so the convex hull will be this tetrahedron, right? Maybe it's better to draw it like here again, so it look like this. And this will be just a unimodal simplex. So it will be different from the example before. This will be a unimodal simplex. So that's a free join. And for instance, that's a nice property here. For free joins, the H star polynomial is multiplicative. You can just multiply them. And we see here, this has a unimodal simplex. H star is just 1 times 1 gives you 1. Okay. All right, so lattice pyramids are free joins because it's just a free join with a point. Free joins are Cayley joins. That's what we understood now. And okay. Now, finally, reducible. So what's reducible? It means that, remember, we have a Gorenstein point. So we have two polytopes. We want it to be a Cayley join on both sides. P is the Cayley join of F and G, and P dual is also a Cayley join of the dual faces. Remember, like you have duality, a face on one side corresponds to a face on the other side, vertex to facet, and so forth. And so if you have this nice property, then we call it reducible. Okay, so it's Cayley joint on both sides. And so here's some to see examples. So if you have a lattice pyramid over Gorenstein polytopes, it will again be a Gorenstein polytop. And that's an example of free joins of Gorenstein polytopes. If you have Gorenstein polytopes, you can just take free joins. The H star polynomial just gets multiplied. If it's palindromic, it will stay palindromic. Everything's nice. Now, free joins are the most important example of reducible Gorenstein polytopes, because if a free join is so strong that it will satisfy this condition on both sides. And reducible Gorenstein polytopes are, of course, Gorenstein polytopes and Cayley joins. And all of this is true. Okay, so you should think about reducibility as somehow like free joins, but a little weaker. And so here's our running example again. Like here we have this P1, P2. We get this guy. That's a Gorenstein polytop, by the way. And this is a Cayley, and it's a Cayley join, but it's not reducible because this is P, and over there's P dual. And no way this thing here is a Cayley. It's no Cayley polytop. Any edge has a point in the middle. How can it be a Cayley polytop? Right? This would have lattice width 1. It would lie between two parallel hyperplanes, nothing in between. It's just not possible here. So this thing is no Cayley. So this is a Cayley join, but it's not reducible. So this example is an interesting example. That's not reducible. Okay, So here's again this conjecture. Now we understand what it means. It tells us that if its dimension is bigger than 2s, it's not just a Cayley, it's a Cayley-Joy. Not only that, it's even reducible. It's Cayley-Joy on both sides. That's what I don't know. It's a pretty recent conjecture, so it could be wrong. Now, there's one important case, maybe prove it there. This is spanning. Spanning simply means that, you know, every lattice point in the Affine-Hall is coming from lattice points in P. So it's an affine integer linear combination lattice points in P. Or in other words, the lattice we look at, like if you have a lattice polytop, you can always look at different lattices, right? It lives in. There are many lattices you can take. If you would take, for instance, here only the lattice spanned by the lattice points of this tetrahedron, it will be a unimodular simplex. By definition, it's a lattice basis. The vertices lattice basis. But maybe this is a reef tetrahedron, if you know them, in dimension 3. That will have arbitrarily large volume. And it will definitely not be a unimodular simplex. So it will definitely not be spanning. It will have definitely not be spanning. So this is a kind of a generic notion. And in, for instance, in the GKZ book, they always assume everything's spanning because they always look at the lattice spanned by the lattice points. Now, if you take spanning and Cayley-Joy, you just get a free join. Because the lattice points, you just take the factors, or the lattice points lie on these two factors, and that's it. That spans the lattice. And so also reducible, if you have spanning, for spanning, really there's no difference between reducibility, Cayley-Joy, and a free join. And it means like, now, what one can prove is that if you have an IDP Gorenstein polytop, the BJ conjecture holds. In IDP case, this is a free join of IDP Gorenstein polytops. So if you have an IDP Gorenstein polytop and D is bigger than 2s, then this reduces, and as it's spanning, IDP is much stronger than spanning. So IDP is much stronger than spanning. Then clearly, if it's reducible, it has to be, it's equivalent to being a free join in that case. So we can actually show this. That's not so difficult, essentially. But it tells you, like, that if you are interested in IDP Gorenstein polytops of a certain degree, and you want to classify them, you really don't have to go that high in the dimension to find all of them. And so the last one here, the second part, is the monotonicity theorem. Namely, you ask probably yourself, why reducible? Why did I come up from this? This is just something I found interesting from some sense, but does it come from? Well, this is really where it comes from. Remember that if you have a lattice polytop, then for every subpolytop, the degree is a monotone. Also for the faces. That's more generally true for each star polynomial. But for Gorenstein polytops, if you have a Gorenstein polytop, you can squeeze something in there. You can squeeze in the degree of the dual face. And you get this inequality. And you get an equality where if and only if P is reducible, and F is a factor of it. So it reduces it into, it's reducible with two factors, and one of them is F. So that's really where this comes from. And in this case, it will always reduce also in Gorenstein polytops. So if you have something which is reducible, the factors will also be Gorenstein polytops. And let's look again at this running example using this characterization to see that it's not a that doesn't reduce. If this would be F and this would be G, then the degree here, this is a unimodular simplex. So this would have degree 0. And this guy here would have degree also 0, also a unimodular simplex. So if you add them out, you get 0. Right? But the degree of this guy, I can actually tell you what it is. The P of T is actually 2. The degree is 2. It's 1 plus T squared stage star polynomial. The degree is 2. So it's definitely less than 2. And so therefore, wait a second. I used a different characterization. Now probably you're saying, what am I doing here? This is F, I have to look at F dual. That's another way to think about it. But okay, we look at F dual. What is F dual? If you have F here, F dual probably will be that one, maybe here, probably maybe this set down there. So these square ones you can ignore. It's fine. So this one is F star. We get, well, in that case, this F star has an interior point. So the degree is the dimension, and the dimension is. So with 0 plus 1 gives you 1, but still it's not 2. The degree should be 2. So we see it's not the case. This is not reducible. Questions? So local H star polynomials. Yeah, try to fix this again to make this. And here's now so many definitions. First, with a localized, and you can just glance over it. If you know them, it's okay. If not, it doesn't really. It's not so important, but I somehow have to mention it here at this point. I know no way around this. So Stanley generalized the notion, the familiar notion of H vectors of simplicial complexes much further to H and G polynomials of lower Lorentz posets. That's a combinatorial definition. Well, if you have a rational point, if you have a rational point with 0 in the interior, so you just realize it like this, then these combinatorial notions have an algebraic geometric meaning, and namely these H polynomials here of their phase posets. So what is this? Where to write there? Well, this is simply all the phases between the empty set and the polytop, but you don't take the polytop. And so this is a poset. You can compute this combinatorial notion, and Stanley proved this will be given by these dimensions of these pieces of this intersection homology and of the associated toric variety. And moreover, the G one, but also G polynomial is defined. This is just what you think it is, namely the differences of the H coefficients. And he shows that the H polynomial has all these nice properties, being palindromic, even unimodal coefficients. So this is strong results by Stanley in his famous paper from '87. But in general, you can do this much more in much more generality. Now, for us, important will be his subsequent paper, the '92 paper on local subdivisions. So, and lots of this was generalized by this really amazing paper of Alan and Eric. So I just give this as a reference. And so they define, so Stanley defines the local H polynomial and using this really weird looking formula. So let's just make sure that you understand what's written there. It's the sum of all the phases in the poset. You have this alternating formula there. Here are the H polynomials. Want to restrict your subdivision onto these phases. And here are the G polynomials of this poset, where the star means the dual poset. You take the poset with your phases between F and P, excluding F, including P, and you take the dual. Okay, and then this is a weird thing. In Stanley's calculus, it can be written very shortly, just as L is equal to H times G inverse. That's what it is. Because essentially this gives you the inverse of G. Okay, so it's like some kind of convolution formula, some kind of, well, that's what it is. And so you can actually turn it around. So naively, you would now like to write, let me see this, H as L times G. And that's actually true. That's what's here. So what's proven is like that H is now simply the sum of all the phases, and you have now the local contributions, that's where the local comes from, of the phases, and then you have this G, this correction factor. And so the L polynomial, so the local H polynomial, also has palindromic non-negative integer coefficients. And even with modality if you add some assumptions to it. So this is a really, really deep result by Stanley. And why did he actually do this? Why do I tell you about this? Because, I mean, his idea was if you have a triangulation and you make it final, refine the triangulation, then you expect that if you look at the H vectors, that the H vector are also monotone. If you add more stuff in, the H vector should increase, or at least not decrease. And that's precisely what he proved using these local H polynomials. That essentially follows quite shortly from these results. In a more, if you use a more generality than just the phase poset we used here, but essentially this was this motivation. And now let's go back to Ehrhart theory. The star guy, right? We have also H star, and there's also an L star now. So here's this definition where you have this sum of phases, and this precisely looks like the one before. Like just again, look at it, stare at it. It's just like essentially the differences here. Instead of an H, we have now an H star. Everything else stays the same. So this is in quite some history. It wasn't if you called L star by Stanley, we will probably find this first in the Katz-Stapledon paper. I wrote an email at that time to Alan telling him like it's kind of should be called like L star because somehow it really is like, you know, it's the analog to this. And so again, the question is, what's its meaning? Where does it come from? And what can we really say about it? And so if you have a simplex, luckily we can be very quick here. If it's a simplex, then it has a nice, all this G thing just goes away because it's always one. So we have this nice alternating formula over all the H star polynomials. Now remember the H star polynomial, I didn't just mention this shortly, the Hi star counts the lattice points on the ith slice on the polypipet. So you take this polypipet, you remove the, you just make it half open, and then you just count the lattice points on the slices, so on the in here. So H1 star would be the number of lattice points in here, and this half open polypipet. And so what is Li star then? Well, you do now an alternating formula, you do an inclusion-exclusion. You start with P, then you exclude the ones on the facet, you include the ones on the edges, and so forth. What you get are precisely the interior lattice points. So Li star simply counts the interior lattice points on height I in this polypipet. So very nice interpretation. And well, in this case, you see it's non-negative. It counts something. There's some nice symmetry in this polypipet, so it could be it's palindromic. And this was conjectured all by Stanley. This should hold in general. And so that was proven by Karu. So for the first time, but actually not really, right? It essentially is already contained in the work by Borisov-Mavlyutov in that paper, and was all generalized again by Alan and Eric. So it's palindromic, has non-negative integer coefficients, and again we can turn it around. Just as before, we can turn it around and get this nice form. And note that in there, since everything's non-negative now, L star of P is in there. It's bounded by H star of P, coefficient-wise, and the G polynomial is also in there. And L star should be really thought of as like the Ehrhart core of your polytop. And so, so there are several proofs here. Like Karu, he uses like combinatorial G theory for this. In the paper by Borisov-Mavlyutov, essentially they use the ring defined by Victor and Cox, and show that this is really the Hilbert series of that ring. And the name you should remember is that in all there are many papers actually we studied already this polynomial, but under a different name. S tilde polynomial is the name that was used at the time, and that was used in many subsequent papers. And Katz-Stapledon now they go further, they refine this, they give a bi- and trivariate version of these polynomials, and they can interpret it algebraically geometrically in terms of so-called limit mixed Hodge structures of these hypersurfaces. And there are some really strong results in there. So very impressive results, also from Ehrhart theory viewpoint in that paper. Okay, so a few words about mirror-symmetry here, or like, you know, again about where does this motivation here to study these polynomials. Apparently they appear in lots of places. So just here's our example again. We have this, let me see, we draw it like this. This is, I think, P2, we have 0 here, we have P1 here. And if you add them together, what do we get? Well, we get, for instance, you get this. Right, so this is P1 plus P2, and that's reflexive. So Minkowski sum is reflexive, and this is what you can use now to define complete Calabi-Yau complete intersections. Namely, you just take each of the hyperplanes and hypersurfaces, intersect them, and you have to be careful that it's non-empty. But if it is, the dimension will be precisely the difference n s minus r, which I call the further n. So S is the dimension we're in. S in this case is 2. R in this case would be 2. N would be 0. Now the question is like, how can you compute these the invariants? Victor and others were interested in like the stringy E polynomial, the stringy Hodge numbers, the E polynomial, and for that Borisov and Batyrev they used the following construction. They looked at the Cayley polytop. So the Cayley polytop will be a Gorenstein polytop. And so you just take a Cayley polytop of these. In this example here, remember this was just the one we always looked at. This running example was the tetrahedron here, which I kind of drawn pretty badly. Anyway, so this is this Gorenstein polytope and will have degree S. Well, in this case, this was 2, and the co-degree will be R as the number of polytopes you had. Right? This is R, this is S. And so here's the theorem rewritten. So this is like this defined formula. In this case, what we say is like if you're interested in this stringy polynomial, like this, where you have these numbers of these Calabi-Yau complete intersections, and you sum them up, and this is what's called the stringy or function first of all, and then, well, it turns out polynomial, and the polynomial can be computed by this combinatorial formula. So this is a purely combinatorial formula, and what you see in there are the L stars of F and F star, so of the face and its dual. So what you do is you go over all the pairs of faces of the Gorenstein polytope, of a pair of Gorenstein polytope you're having, right? So and you take all, you always multiply these, and you have these, of course, you have all these vectors in there you have to be careful about. And the one vector, which is kind of one which is like, which really kind of messes up in some sense, well, it's like that you divide by uv to the r, and it's a priori not clear that it's really a polynomial. But of course, this is just a formula. You only know now it's a polynomial, this combinatorial invariant, if you have a Cayley polytope having in the first place, and it has also the right number of factors, namely precisely the co-degree. In general, a Gorenstein polytope doesn't have to be a Cayley polytope. And what about this? Is it still a polynomial? The answer is yes. And wait a second, before I do that, here are some more properties here. So these are nice properties satisfied by many properties, also conjecture properties, and this is like the these are these dualities in there, and the mirror symmetry. What I was referring to at the beginning, like, is this relation here, where we have on the one side P, on the other side P star, and you just have these little changes in these variables that you can transform one to another, and this can be nicely visualized by looking at a Hodge diamond. And so what I was saying is like that this combinatorial formula also makes total sense for arbitrary Gorenstein polytopes. Right? Where just no further assumption, you can still write down this combinatorial invariant, and it will also be a polynomial. So this is what's that result, and that means like if you look precisely of this form, so you can essentially get assigned to a Gorenstein polytope combinatorial string Hodge numbers. So this is just combinatorially. And then we'll all satisfy these properties down there just because these are combinatorial properties. And the proof is essentially not so hard. This follows from the monotonicity result I was telling you about, that the degree of f plus the degree of f star together is at most the degree of the polytope. If you plug that all in and look at it, you will get that this is a polynomial. That's precisely where this result comes from. Okay, and all right, so coming now to the last part of the talk, and I hope I'm not too long. I hope that I can talk. I mean, I really don't want to go any overtime, so please interrupt if you tell me this is totally unusual how long I'm talking here.
No, it's not unusual. It's okay.
It's okay. Thanks. Okay, thin polytopes. So what does that mean? So the definition is simply that the local H star polynomial vanishes. Remember, it's a non-negative coefficients, but they can all be zero. It's totally possible. And equivalently, remember, these are all non-negative integer coefficients. So if you sum up all the coefficients, well, if the sum of the coefficients is zero. And for a simplex, now we have a nice interpretation, right? If you have a simplex, then L star was just counting the interior number of points on the slices. So if you sum them all up, you just get the number of interior points in the whole parallelepiped. And this was called, and this notion, so essentially like the story here is that in the GKZ book, they introduced the notion of thinness. They look at simplices, they say it's thin if this alternating sum is zero. But there they don't think about the combinatorial side to it, so they don't use this interpretation in terms of the parallelepiped. So they have to do some very deep algebraic geometric results and methods to really prove that it's, for instance, non-negative. Even in the simplex case. And so this is the Newton number from their motivation, so in their setting. And so they actually explicitly write the following, that there's like an interesting problem in geometry of numbers to classify these thin lattice simplices. So their motivation came from the study of regular A determinants, the question when they are equivalent, and in there naturally these thin simplices somehow appear. And now what we say is, well, this is also interesting for polytopes. And I hope it can give you more motivation also. So let's just look at this. So in dimension 0, lattice point is just thin. And if a dimension is bigger, so D always the dimension of a polytope, then the L star of D, like the leading, so the L star, maybe we should say something about it. So L star, it's palindromic, right? And it will always look something like this. So the zeroth and the D plus 1 is 0, and then there's this palindromicity here. So it's palindromic here in the middle. And so, of course, these coefficients can all be 0, but we have this equality here, and like LD star, which is L1 star, is the number of interior lattice points. And that's easy to see in the simplex case and it falls in general. And in particular, this means if this is 0, it just means there are no interior lattice points in a polytope. And so thinness implies that it has no interior lattice points. And one example, to give you one example already, is these are lattice pyramids. Whenever you have a lattice pyramid, this will be automatically thin. In dimension 1 and 2, actually, having no interior lattice point is the same as being thin. There's no difference there. This is also proven in the GKZ book for in the case of simplices, but it holds in general. So the first interesting case is dimension 3. What happens in dimension 3? And so we proved this like that in dimension 3, it's thin. Well, there are two cases essentially. Either it's just a lattice pyramid, we already know that, or the degree is at most 1. And these can be easily classified. And you might think, maybe that's something to generalize. And indeed, right? So there are two ways how we can generalize this. The first one is we can say, okay, if our polynomial has the degree of a polytope of H star polynomial is at most dimension half, then we call this trivially thin. So why is this thin? If we have this condition, it will be automatically thin, because think about now your coefficients of L star and H star. So we have 0, we have D, 1, and so forth. And so until here, until we have, and somehow we have L star, we have H star. When H star is only at most degree here, so there's only something here. The H star polynomial has only coefficients up to the half of it. Now L star, remember, is smaller. It's at most H star coefficient-wise. So somehow, if you use red for the L star guy, maybe something here. Well, here's L star. So there would be some in L star, because it's palindromic, it would flip up here. Get something up here. But wait a second, there's no H star there. And L star is at most H star. So H star is at least L star. There has to be something else. It doesn't work out. That gives you a contradiction. So if the degree is smaller than D half, then it's trivially thin. And let me just actually tell you that we can rewrite this in the following way. If the degree is S, that simply can be written like this. And maybe we have already seen some of these bounds before, right? Okay, the other case, so this is the first case. Degree at most 1 in dimension 3. So that means like the degree is at most 3/2, so 1/2, so 1.5, so it's at most 1. Now the second one is the lattice pyramid, and that's just a special case of having a free join. Wait a second, I have to kind of lower my table here. So, all right, so we need. So if it's a free join, where one factor is thin, why is that? Because if you have a free join, not only H star, but also L star is multiplicative. If you have a free join, then L star of P is simply the product of L1 star and L2 star. So if L star of P1 times L star of P2. So if one of them is 0, the whole thing will be 0. So whenever you can take a free join, you can just take thin guys and you just take a free join of it and you get something thin. And that's precisely for lattice pyramid. A point is thin, so if you take a free join of it, it will be a lattice pyramid. So these are the two ways we know of how to construct in high dimension thin guys. And now, of course, we were wondering, what about the converse? by looking quite hard, we finally found some counterexamples by just looking at databases and computing examples. But the following is still open, and it looks kind of interesting. That's like if you add spanning to it. Remember, spanning was this generic case that the lattice is spanned by the lattice points in the polytope. Then we do not have any other example. It would be very interesting to see if this is really all the constructions we're having. And of course, now let's go back to Gorenstein polytope. And the answer in the Gorenstein polytope case is yes. If we have a Gorenstein polytope, then it's if and only if P is trivially thin, or it's reducible with a trivially thin factor. And remember, if we add spanning to this, reducible simply becomes free join. So the answer to the previous question is yes. And we can add more to this. This thinness property is invariant on the duality. If the P is thin, then P dual is also thin, and vice versa. And so this is a very nice, from a viewpoint of this mirror symmetry thing. And if you have thin Gorenstein polytopes, they are always Cayley's. You might ask why. Well, here it is. If it's reducible, it's much stronger than Cayley, right? It's a Cayley join, the dual is a Cayley join, definitely a Cayley. And if it's trivially thin, well, this means the dimension is at least 2s. And there was this Cayley result. I showed you the proof, or I tried to sketch you the proof of. It showed that if d is greater than 2s for Gorenstein, it's a Cayley polytope. So thin Gorenstein polytopes are always Cayley polytopes. And finally, I will also tell you a bit about the proof there. If you have a thin Gorenstein simplex, it has to be a lattice pyramid. And this answers this question of Gelfand-Kapranov and Zelevinsky about thin simplices in the case of Gorenstein. So what are kind of some open questions here? Well, it's if you have reducible thin, you don't know of an example where we really need reducible for thinness. In general, it's a notion you cannot just discard, but here we just don't have an example that's not just a free sum. Is that hinting at something deeper or not? Probably, I don't know. And also the L-star polynomial is multiplicative for free sums, right, of Gorenstein polytopes. But what about if it's just reducible? That would be very interesting to know if that's true or not. And so the last two slides about the proof and what's like behind this, and I also will say one more word about where the star actually comes from, we always use. So the actual proof is something the following. We define G thin that the G polynomial has the same degree as the H star polynomial. So the degree of H star polynomial, degree of its G polynomial, like of the phase poset, is actually the same. Now remember, the G polynomial always has small degree. The degree is at most half of it, almost half a dimension. So by definition, the G thin is stronger than trivially thin because it implies trivially thin. That's namely because the degree of the G polynomial is so small. And so the actual proof is this. It's thin even though if P is G thin or reducible with the G thin factor. And so the proof lies, of course, on this reducibility characterization by degree. And it also relies on the fact that if you have a reducible polytope and the factor is a lattice pyramid, the whole thing is the lattice pyramid. And that really uses reducibility very strongly, because in this running example we were having, which was not reducible, well, every factor was just a model simplex. It was definitely a lattice pyramid, but the whole thing was not. So we really need reducibility there. And using this, we can already prove the stuff about thin Gorenstein simplices. Because what happens if we have a simplex? What's the G polynomial? It's just 1. The degree is just 0. Meaning if it's G thin, the degree of the H star polynomial is 0. It's a unimodular simplex. And so let's talk out. And on the other hand, if it's so it's a lattice pyramid. On the other hand, if it's reducible, and one of it's a G thin factor, so it's a Gorenstein polytope, it's a G thin, again by induction, it will be a lattice pyramid. And so by this result here, the whole thing will be a lattice pyramid. So it directly follows the result about the simplices. And we need to prove further the fact that the degree of the G polynomial is invariant under duality. So if it just for polytopes in general, if we have put the degree of it and look at the dual polytope, we can do that purely combinatorially. The degree of the G polynomial will be the same. So this is a result by Calabi-Yau. And finally, we need something which just seems to be very simple, but it's actually not. It follows from that's the last slide. I want to mention this. If you coarsen the lattice, so you make the lattice coarser, then the L star polynomial think about the simplex setting and where it counts something, of course, it counts less lattice points. So it should, previously it was thin, like L star was 0, and it should still stay 0. And it's true, but why is that the case for polytopes? And that follows now here from the last slide. There are these beautiful results by Katz and Stapledon. So take a polytope and divide it and put it. Oh, okay, no, that's wrong. We don't need lattice simplices, just polyhedral subdivision. And now, what you can do is you can take the famous Batyrev-Juny formula that the H star polynomial, it can be actually computed by knowing the box polynomials, so the L star polynomials of all these faces of the cells of the subdivision and the H polynomial of the links. This was proven for triangulations by Batyrev-Juny. But actually, it's true in general for any kind of subdivision. And so we see that the H polynomial of the subdivision is at most the H star polynomial. And actually, we only have equality if and only if all the faces are thin. So again, here thinness turns up very naturally when we've been characterizing this quality here. Now comes the thing, like think about it. We had H and we had L. Now there was H star. Now you see where H star really comes, and we can see it from here because the same thing was true for H. Because it's true for H if it just remove the stars. And now this was like from the formula as I showed you. So you just write a star here and see, and you get this. And here we have L star. And remember, we also had a formula how to go from L star to H star. And so my question was at one time, well, there should be a way to go from here to here. If this is really L star, then this there has to be a way how you can generalize this. And it's actually easy to write down, but hard to prove. And this is really proven by Alan and Eric. We have this, look at this H star, L star, H. Now we have L star, L star, L. It's the very same thing. And these guys are called relative local H polynomials. And the hard thing to prove is that this is non-negative. And I use like decomposition theorems and to prove this. And that has the but using this, we get the current sequence we want. But thinness stays invariant under causing the lattice. Because see, what they do now is just take a triangulation. And here they're all then simplex. The F is just a simplex. And for simplex, we're counting something. If we cross the lattice, we will count less. And since everything here is non-negative, everything's non-negative. If you count less and everything's not, you just take less here, but everything else stays the same and it's non-negative. Well, in total, if it was 0 here, it will still be 0 if you add less to it. Okay, so this will be, think about it, just follows directly from its formula because the only thing that changes is this guy is the red guy here. And since everything's non-negative, it follows. So the last two comments. One is like if you have a regular unimodular triangulation, but actually, yeah, well, then L star is of a polytope is simply by this formula given by the local H polynomial. And L star is simply the local H polynomial. So L star is simply L. And Stanley proved using Hart-Lefschetz, intersectional homology and stuff, he used that this is unimodal. So they see like if you have regular model triangulation, L star is unimodal. And what Johanna and the authors of this paper are looking at is also what happens if you have an IDP. You just substitute this by IDP, then this should still be true. And finally, if you have a thin polytope, all the triangulations are thin, right? This is a non-negative, all this L will be thin because of the formula above there. And so in particular, thinness means that the local H is 0. And there was lots of interest, there can't be lots of interest in these triangulations. And especially there's a really deep results, really intricate, long paper with very complicated proofs by, again, also by Alan and others, where they look at these thin triangulations and show that they improve results about them and show that that proves the what's local motivic monotropy conjecture. You probably know more about this than I do. So, so the question would be really if it's maybe we'll get some interesting combinatorial restrictions out of their results. And that's the last thing I want to say. Sorry if that was a bit long. I hope this is okay. Thanks so much.
Okay, let's thank the speaker, first of all. And if there are any questions, please feel free to ask them.
So what is known about the focal vector of an IDP polytope? So let's say I'm looking at the generating set for the canonical module, right, for the interior comp. Is there anything known about the graded pieces of this generating set? Can they be far apart? Can they be yeah, I mean, is there any interpretation or any result concerning that?
I don't think so. I don't think I'm not aware of anyone really who really looked at this. I mean, you're really talking about general IDP, right? One should probably first like ask people right really in the commutative algebra community where they looked at this. The question here really is how much you need where kind of, you know, where really does the combinatorics come in this comes in. So I don't know. So from the combinatorial viewpoint, I know that, so like from a polytope setting, I don't think people looked at this.
Yeah, definitely the semigroup structure has to come in this. Yeah, I mean, I'm just asking because I mean, if there's a counterexample, it has to kind of come from there. So,
definitely, yeah, that's.
But a counterexample for general IDP.
Yeah, I'm not aware of it. Sorry, I said don't know.
Thank you.
I mean,
thank you for the nice talk.
Thanks. I mean, like there's a long time, like no one really, you know, if you look at the results I showed you, there was quite a big gap of time, and people will look more closely at more concrete cases. But I mean, you know, also results by Stanley, and like they, you know, I think there are not many follow-up papers essentially. They really proved about this. I guess like one of the experts really is like Christopher Borger still about these questions, at least from a combinatorial viewpoint about the local age. Yeah, so I don't know. I mean, it feels like to me that not many people actually thought about it, because in general this was actually considered to be quite hard, I think, with this machinery, and it wasn't clear how to proceed. So I think now probably there will be new incentive to do that.
I also have a question. For the reducibility or Cayley-ness, how much do you get if you assume only IDP, not Gorenstein, not smooth?
You have only IDP for the.
If you have only IDP, are you only left with the
so reducibility, the trouble is really like you first have to think about how do you define it. Like, you know, you can use Cayley join, you know, because you don't really have a dual. Somehow.
Yeah. Okay. Fair enough.
That's
okay,
the problem.
But I mean,
like,
even just for Cayley, do you get more for IDP than you do for general?
Say again. I'm sorry. Like if you for what? I'm sorry.
Do you get closer to the Cayley conjecture, assuming IDP,
the Cayley conjecture in the case of IDP,
than the general sort of case of?
Yeah, I haven't thought about it. So I think like the Cayley conjecture for IDP is so without Gorenstein.
Yeah,
I think it's still open. I don't know.
So there, the best known bound would be the same one that you have for general polytope?
Maybe a bit better, but so the base, so the bound we're having is like quadratic, and the first, so it would be good already to have something linear. And it could be that maybe for IDP one can. I don't know. I mean, I don't know if I ever really tried how hard I ever tried, but I mean, like this is yeah, it would be even good there to have it.
Okay, any other questions, comments, complaints, anyone? If not, I stop the recording. Oh, no, okay, Vladislav, go on.
I just want to ask, do you have an example of Gorenstein polytope that is not Cayley? We don't add finesse.
Go to further, but it's not Cayley. You can, for instance, I mean, you could, for instance, you could take two deltas of 3, so you just take twice the unimodular tetrahedron in dimension 2, and you make it twice as large. So that one will be Gorenstein. And as it has lattice points in the interior, it won't have. Actually, we've seen it already. Let me just show you. Where's it? There was this one picture. Okay. Here it is. Yep. So that one here. That is essentially that. You see, it's also Gorenstein polytope because it's a dual. There's a Gorenstein polytope, but that's not a KD. Right? It's just lots of points in the interior of edges.
Thank you. And also I want to ask a question that I have an impression that Kelly polytopes convex house of dual defective sets. Dual defective set, it is a set for which the dual toric varieties not have a surface. And maybe you know something like, is it true?
Yeah, I mean, there's this connection that if you have a well defective such a polytope, then and you say it's spanning, right? This is a typical situation. Then it's Cayley. Yeah, that's known.
Thank you.
So defectivity implies Cayleyness there. That's I see that. Not sure, but I think Alex Estorff could be. I'm not sure if I've seen him, so like he's like the expert on this, and yeah, so that should be the case. And there's a complete, very interesting characterization of dual defectivity also by two authors. I'm not sure,
Furukov and Ito.
Yes, thanks, Alex. And so that is very closely related in some sense to these questions, like from the flavor of the results. That is, we also strengthen Cayley in a certain way so that it fits.
Okay, if there are no other questions, I at least turn off the recording. Right.